The next chapter is the chapter on kinetics. And kinetics is a study of how fast reactions occur. One would call them the speed of the reaction. The best way is to call it the rate of the reaction. How quickly is the reaction going to happen? There are some reactions that are extremely fast, are done in 1 times 10 to the minus 12th of a second. There are some reactions very, very slow, take 20 minutes, 30 minutes, take years. And so kinetics is a study of the rate of reaction, how fast reactions occur. All right, so a few things in this chapter. Since kinetics is really very heavily involved in a bunch of other areas of chemistry, we're going to introduce some terms that we're not really going to look at in depth until some future chapters. For kinetics of the reaction, we're looking at reactions that do go. They do go, try to go to completion. These are spontaneous reactions. There's a term called delta G, change in Gibbs free energy, that talks about that. We're going to look at that in more depth in the next chapter. But these reactions, at the end of the semester, this video will make more sense, have large negative delta G values. They go to completion. Okay, of reactants going to products. So the first thing is, let's look at the rate of a reaction, and we have to define what we mean by the rate of reaction. So let's look at a very general reaction of reactant A reacting to form product B. Well, the rate of the reaction is how fast it goes, okay? And there are two things you can look at. How fast is A going away? How quickly does reactant A react? And the other thing we can look at is how quickly is product B forming? How fast is B coming to be? So the rate of reaction is the change in concentration of B, our product, with the change in time. How fast are we making product? And the amount of product, since it's going to be dissolved in a solvent, the amount of product is looked at as the concentration of that product. So the change in concentration of product, how fast is B coming into being, how fast is B getting more concentrated with respect to time. But note, at the same rate that B is coming into being, A is leaving, because B comes from A. For every one B that gets made, one A goes away. So the change in concentration of A over the change in time will also give you the rate. However, since A is going away, we have to compensate for that with the negative sign. So when we're looking at the reaction A goes to B, we can monitor the concentration of A and realize the rate is negative, change in concentration of A with change in time. Or we can monitor product B and note that the rate is a change in concentration of B over the change in time. Or we can monitor both, and they should give us the same rate of reaction. And when we do this, we find something interesting. If we look at a graph of concentration versus time, what we see here is, since this is the high concentration up here, we know that this point right here is, or this line of here represents A, our reactant, because there's more of it at the beginning, and this down here is B, our product, since there's less at the beginning. What you notice about this graph is these aren't straight lines. It's not that A goes linearly down to nothing. We've got this type of function here. It's actually a logarithmic function. And so note, at the beginning of the reaction, A is disappearing quickly. The concentration is changing quite a bit, and not much time is going by. However, as a reaction goes, the rate of reaction is slowing down. The reaction is slowing down. So look, over this amount of time here, there was not that much concentration of A going away. If we look at the concentration of B with the change in time, we'll see since A is going away very fast at the beginning, B is coming into being. That product is forming very quickly at the beginning, but then the amount of product that you get gets lower and lower in terms of more and more product. It's not coming into being quite as fast. And these two eventually become asymptotic, and they are going to get even with these lines, with the lines down here, and theoretically will never touch. Okay, so let's look at this. Let's look at an example reaction down here and see what we can see. We're going to run the reaction of bromine, Br2, with formic acid. And so here's the reaction we're going to run. Br2, dissolved in water, aqueous, plus HCOOH. That's our formic acid. It is also aqueous. When we run this reaction, we find we get 2Br minus plus 2H plus CO2 gas. Note, HCO3, formic acid, bromide ions, H plus CO2, these are all colorless, clear colorless. However, Br2 is a reddish brown, kind of orangish molecule. So when we start the reaction and we let it go, what we should see is, since we start with aqueous bromine, we'd expect our reaction to be orange when we begin with, because Br2 is orange. But what do you expect to see in our reaction flask as the reaction continues? Well, the orange Br2 is going away, forming colorless things, so we'd expect to see as the reaction continues, the reddish-brown color gets lighter and lighter and lighter, and if the reaction were to go all the way to completion, we would expect that there would be no more color, no more reddish-brown color at all. That's what we'd expect to see. Now, the interesting thing about monitoring the kinetics of the reaction is you've got to find something to monitor. Now, the good news is there's lots of stuff we could, in this reaction, we could monitor how much bromide ion there is at any time, but that's not easy to do. Ooh, 2H plus, perhaps a pH meter, we'll discuss that later this semester, might monitor the reaction. I don't know, gas pressures might do, but we've got a nice system here in that with Br2 being a reddish brown color, we can use visible spectroscopy to monitor this reaction. During the semester, hopefully you'll be doing some experiments using Beer's law that looks at the absorbance of a solution that has color in the visible wavelengths. And that tells us concentration, because how much light is absorbed by your molecule equals a constant times how the distance that the light is going through the sample times the concentration of the sample. So basically what we're saying is how much light gets absorbed by the sample is proportional to the concentration of the sample. At the beginning we have a higher concentration of Br2. It's kind of a darkish reddish brown, darkish orange. It's absorbing a lot of light, that gives it that color, and we know that its concentration is high. As the reaction goes, the concentration of Br2 goes down, and so the amount of absorbance goes down, the color gets less and less strong. It gets weaker and weaker. And with the proper instrument, and your book has a diagram of the instrument, and using the math of Beer's law, we can calculate the concentration of Br2 at any time based on its color, how strong the color is. And so we do that. And so we say, okay, at time 0, this was our initial concentration that we put in there. After 50 seconds, we measure the absorbance, find that here's the new concentration. After 100 seconds, there's a concentration. After 150 seconds, there's the next concentration, all through Beer's law here. And if we plot that, as I showed before, we get this red curve here. But the question is, what is the rate of the reaction? Okay, we can see that after 150 seconds here, the concentration has dropped quite a bit. But is the reaction over? Well, I recall this is kind of asymptotic, so is the reaction ever mathematically over? Even though, practically speaking, it ends. How are we going to get the change in concentration with the change in time? Well, we can do it a number of ways. I mean, this is literally just the final concentration of Br2 minus initial divided by the final time minus initial time. That gives us the slope of a line. And since we are monitoring bromine, which is the reactant that's going away, we have to have the negative sign here. But we have a problem because, all right, here we've got a table of various times, a table of various concentrations. I can say what was the rate from time 0 to time 50. So that would be the final is 50 minus 0, and then our concentration, final concentration minus this concentration, take the negative of it, and that will essentially give me this line right here from our initial to there. So it's the slope of that line. But if I decided, no, what about from 0 to 100, I get a different line with a different slope. And 0 to 150 gives me another line with a different slope. All those then are different rates. Since the rate is the slope of the line, the rate depends on the time interval we change. And heck, we could have gone crazy. Well, what about the rate from 50 to 100? What was the rate during that time? And so what we get when we're doing it this way is we get average rates. And the average rate of a reaction, we have to look at the time intervals. Are you talking about from 0 to 100 seconds? Are you talking about 0 to 50 seconds? Are you talking about 50 to 100 seconds? Because all those different intervals will give us different average rates, which makes determining the average rate oftentimes just not that great. Okay. So, is there a way, though, that we can look at this and get some better data? Well, let's take a look. What if we did this? What if instead of the average rate over a definite variable of time, like 10 seconds, 50 seconds, 100 seconds, what if we decrease that time? Let's 10 seconds, way too long. 5 seconds, still too long. Let's look at the change of rate after 1 second. Guess what? 1 second, still too long. How about every 100th of a second? Still too long, but now we're having trouble. How do you measure these at 100th of a second? And the answer is you can't unless you know some calculus. If you remember calculus, what we are doing here is looking at the change in concentration divided by the change in time as delta t approaches 0. Oh, you remember that type of stuff? What is it? Change in something over change in time as the time goes to 0, limits. Yeah, we're heading towards derivatives here. We're doing calculus. Good news or bad news, depending on how much you like math, we are not going to do actual calculus in this class. We're just going to give you the results of that calculus. However, what if we did this? What if we were looking at the change in time getting smaller and smaller? Let's say we start at time here, end at time here, but we shrink this time axis. We bring these two pieces closer and closer and closer together in the limit where delta t, change in time, equals 0. We can do, if we know the equation, if we plot this graph, take the data that we made before and plot it, fit an equation to that line, then just have a computer do the calculus for us. We can actually calculate this value right here. And that rate, that instantaneous rate, the rate of the reaction when delta t approaches 0 at this time, is essentially the tangent line to this curve. Here's our curve of our data. Here is the tangent line to that curve. That is the instantaneous rate that you would get through calculus. All right. However, if we look at that, we can see that, okay, at this point right here, our tangent line looks like that. But at this point up here, our tangent line is more like this. And at this point down here, our tangent line looks like that. So even these instantaneous rates are going to depend on where in the reaction you are looking at. Are you close to the beginning? You expect the tangent line and the rate to be faster. Close to the end, the rate's not going to be nearly as fast. And so we decided that, you know what, there is one point that all reactions have in common, and that's the initial point. Right at the very split second when the reaction starts. What if we measured the rate of the reaction at exactly when it begins, at that the instantaneous rate at time equals 0? That tiny, tiny fraction, it's even less than a fraction of a second. It's an instant when the reaction started, when time equals 0. Because what we have found, if your reaction is very, very slow, that instantaneous rate at time equals 0 will be a fairly slow rate. If your reaction is really, really fast, the instantaneous rate at time equals 0 will be a fast rate. So we can use the instantaneous rate at time equals 0, how fast the reaction kicks off. We're going to call that our initial rate, and we can use that to measure how fast reactions go. To get an idea, is this a fast reaction or a slow reaction? We look at the initial rate. Okay. So let's run our reaction again. We ran our reaction with our bromine. Note, we ran our reaction with our bromine. We got this line here, right here. Technically, to get the instantaneous rate at time equals 0, we have this data, we graph this data, we then apply calculus to that graph, and then we can calculate that instantaneous rate with the computer. A lot easier to do now than it was when these ideas were being formulated. All right, but we're going to run this reaction, but we need to cheat a little bit, because as we're going to find out, the rates of reactions can depend on our various reactants. Note, for the reaction we're running here, we've got two reactants. We got bromine, Br2, and formic acid. We have those two reactants. And I'm interested in, okay, how does the rate depend just on bromine, just the Br2? How does the rate depend on just Br2? And the problem is, well, what if the rate, we're going to find out later whether it does or not for reactions, what if the rate depends both on bromine and on this stuff here, the formic acid? How do I make sure that when I'm looking at the rate of reaction, I'm just looking at the rate responsible due to bromine? And the way we do that is, since we know that the rate is the change in concentration with the change in time, we set our conditions so that the concentration of formic acid doesn't really change with time. And we do that by adding a large excess of formic acid. If you only wanted to look at this reaction, the kinetics of the reaction with respect to bromine, you have such an excess, 1,000, 10,000 times more formic acid than you need, such that any changing of those rates of the reaction depends only on the bromine, because the concentration of formic acid is not going to change if it's 1,000, 10,000 times the concentration of bromine to begin with. Note, for future knowledge, when you calculate the rates and the rate laws that we're going to get to later, when you do that, we call these a pseudo rate law or a pseudo rate constant, because it's not the actual rate constant of our reaction, because we changed it such that one of our reactants didn't play a role in the rate. However, that's okay. We're going to put a large excess of the formic acid so that the reaction rate doesn't depend on it. The change in concentration of formic acid with the change in time is essentially 0. There's essentially no change in concentration because there's so much of it, and only a little bit is going to react with the bromine. So then we run our reaction, get our curve, plot it, do some calculus on it through a computer is the best way, and you get the instantaneous rate at time equals 0, our initial rate. And actually, you can get a bunch of different instantaneous rates at different times, and when you do that, if you were to calculate the rate of the reaction versus the concentration of Br2, you'd find this is a straight line. When the concentration of Br2 is very, very high at the beginning of the reaction, we have a very large rate. When the concentration of Br2 is very low towards the end of the reaction, we have a very low rate. And from this graph, we can see that the rate of the reaction is proportional to the concentration of Br2. It's a straight line. Well, how does one make a proportion? How does one change a proportion sign into an equals? You have to add a constant. And so what we have here, the rate of our reaction is going to equal this constant. We call that the rate constant, times the concentration of Br2. Note, this rate constant is not affected by Br2. Note, the rate constant is the slope of this line. Remember the equation for a line, y equals mx plus b. Y, the rate, equals m, the slope of the line, but here that's k. X is this axis here, concentration Br2, and B is 0, since if there's 0 bromine in there, our rate is 0. So this is really just the equation for a straight line, y equals mx, where our slope of the line m is our rate constant. All right, cool. What are the units of this rate constant? And that's going to be an more interesting question as we move on through this chapter. Well, what are our units of rate? What are our units of concentration? Well, rate is the change in concentration with the change in time. That is molarity divided by time. And units of time is seconds. So rate is molarity per second. Concentration of Br2 is molarity. And so divide both sides by the concentration of Br2 to get K by itself. We see the rate constant equals rate divided by the concentration of Br2. The rate constant equals molarity per second divided by molarity. The rate constant is 1 over seconds, or seconds to the negative 1. All right. Because of this straight line here, and they're not always straight, the rate constant has the units of seconds to the negative 1. A little glimpse into the future here. This is a first order reaction, and anytime you have a first order reaction where the rate is only dependent on the concentration of one thing to the first power, something we'll get to, you will find that the rate constant has units of seconds to the minus 1. Okay. So, now we looked at our reaction rate depends on the concentration of reactants. Change in concentration of reactants with change in time looks at its rate equals a change in concentration of products with the change in time. But how does stoichiometry play into this? Well, what if we had 2A goes to B instead of just A goes to B? Well, note now 2 moles of A will disappear for every mole of B that forms, which means A is disappearing twice as fast as B is forming. However, mathematically, it's the same reaction. Whether we're looking at A or B, we must come up with the same rate. So how do we contend with the fact that A is disappearing twice as fast as B is forming? Easy. We divide it by 2. So our rate of the reaction equals the change in concentration of B with the change in time, because B is the product, equals negative 1/2 the change in concentration of A with change in time. Negative, because we're looking at A and A is the reactant. 1/2, because since it's 2A goes to B, A is leaving twice as fast, so we need to divide by 2 to get rid of the fact that it's leaving twice as fast. So, in general, if we have a general reaction, A moles of A plus B moles of B goes to C moles of C plus D moles of D. Hint, you're going to be seeing this general reaction all the time this semester. A moles of A plus B moles of B goes to C moles of C plus D moles of D. The rate of the reaction would be 1 over little a, 1 over the stoichiometric A times the change in concentration with the change in time. That will be the same as 1 over little b times the change in concentration B with the change in time, equals 1 over little c times the change in concentration C with change in time, equals 1 over little d times the change in concentration of D with the change in time.